saddle point is you'll pick out the higher values, like it depends on whether it is your row or column. Okay, so here if you see that you didn't, though you had a saddle point, we had to reduce the dominance strategies by means of which all your column values are higher than the second column here. Okay, so you can eliminate your first column. Okay, so similarly here if you take the rows, all the values given here 9, no, which one is higher? Yeah, A is greater than C and B is greater than C. This is for column, and for rows, yeah, 2 is greater than 1. So 2, 9 is greater than 6, 7 is greater than 5, minus 2 is greater than minus 4. So you should have a row or a column which has got all the values, not just one value, all the values of that row being higher than the values of the other row. Okay, so in that case, you have to eliminate the row wise, you have to eliminate the lower values, and column wise you have to eliminate the higher values, right? Because these represents your column represents your loss and row represents your profit. Okay, so once this is done, that is called as reduced matrix. And after you get the reduced matrix, what you have to do is, what is the best strategy that has to be followed. So you have to choose the best strategy. So for the player 1, um, yeah, this is player 1 and this is player 2. So you have to choose, player 1 is going to choose the 2, the second strategy, and for player B, the second play this side, right? So for that player, he has to choose the strategy C. So this is how you finally reduce the matrix and come to a conclusion. So this is what was the last class. Now moving on, we also saw something called as dominance system. Okay, prisoner's dilemma was also seen last class. What was prisoner's dilemma? You had two people who are suspected to show that they have, you have to prove as a lawyer or as a police officer, you have to prove that one of them has committed a crime, or if none of them accepts that they have committed a crime, both of them must be let free. Okay, if one of them accepts, that approval will be given less punishment and the other person will be given more punishment. Okay, so accordingly you derive at the prisoner's dilemma matrix. Okay, so this prisoner's dilemma matrix, it is applicable for many other applications also. Okay, so till this we saw with the last class. So if both the person refuses, both will be getting minimal jail of 1 year, and if both of them turns out to be approval, both of them will get again minimum but not very less compared to both of them refusing. So both of them getting 2 years. If one person becomes an evidence, in that case he will be getting 0 year and the other person will get 3 years. Similarly, vice versa here also happens, right? So till this we saw in the last class. Now we have to go on and we have to see what is called as mechanism design. So it's another very important concept in game theory, which is called as mechanism design. Now we saw about various concepts saying that if I am McDonald and if the other person is KFC, what is the strategies that we play? Okay, so that strategies, uh, here, let us say, one second, I'll come back to this later. Right. I'll just complete this, when then we'll go back to that. So if you have KFC having two strategies, so this is one strategy, the B is another strategy. Similarly, left and right here also, McD is playing a different strategy. So depending on strategies, we saw that these values, whatever you get here, these are called as your payoff matrix. Okay, so when you have a payoff matrix, you should decide, or at the end of the problem, you should be in a position to say that whether you have, here you're not going to talk about saddle points, you're going to talk about something called as Nash equilibrium. Okay, so what is Nash equilibrium? Whether the strategies played by both the players, player A and player B, whether they are having any equilibrium points, whether that strategy is good or bad. Okay, so if you have a Nash equilibrium, You can have one Nash equilibrium or you can have more than one Nash equilibrium. That is not a point. Okay. But whether the problem has a Nash equilibrium or whether it doesn't have the Nash equilibrium is what we are going to determine. Okay. So we'll come back to this problem later. We'll go back and now we'll see about what is called as okay dominant. Okay, so what is a game? We know that you should have a number of players. The payoff matrix is nothing but the outcome of the game, which is represented as profit or loss or utilities. Okay, so these are the basic terminologies that you have to know. And the game, both the players must know how to play, and each one, depending on the strategy they choose to play the game, they are going to either win or lose the game. So accordingly, they are going to get a payoff matrix. Okay, so now if you have this game player A and player B, so these are called as your payoff matrix. Okay, so 3-0 depending on this is player A strategy. 3 is the player A playing the top strategy and player B playing the left strategy. The utility that player B is going to get is 0. This is how you have to read this table. Usually you'll have one value here, three, like some solid values, but here when you're given like this is nothing but player A's top strategy, player B's left strategy. Okay, so this is how you have to read it, and this is player A's top and player B's right strategy. Okay, this is player A's bottom and player B's left strategy. Player A's bottom and player B's right strategy. So this is how you're going to read the problem. That is, this is how you read the payoff matrix. Okay, then moving on. So here, what is dominant strategy? This we have already seen. So what is dominant strategy? If one strategy can be eliminated from the other strategy, okay, by saying that the profit of all the values is higher than the profit of the second value, right, other strategy, so that is going to be called as your dominant strategy. Similarly, the loss values of one strategy is less than the loss value of the other strategy, that can be eliminated. Okay, so these are all the rules of game playing. Okay, now what is Nash equilibrium? Nash equilibrium is the optimal choice for both A and B. Okay, so you're going to select something which is going to be optimum for both the person. Say for example, in our prisoner's dilemma problem, I can say that the Nash equilibrium is nothing but you understood the prisoner's dilemma problem, right? So what would be the Nash equilibrium here? If both of them they don't say silent, actually they accept, in that case they're going to get 2 2 years. No, that is not a proper thing. Or the other way is both of them staying silent is also a Nash equilibrium, right? Because both of them they're going to get minimum punishment. Okay, so in that case you'll be having two Nash equilibrium values, right? So here in this case I'll tell you how to find out the Nash equilibrium. Okay, so here suppose if I say this is one Nash equilibrium and this is another Nash equilibrium, how do I derive at this? That is important, right? So first take the first, these two rows. Okay, for player A's you just have to listen to this. For player A, okay, you just compare player A's strategy is top and bottom. Okay, so comparing for player A, 1 2 you have, which is higher, 2 is greater than this 1. Okay, and you can also see that this 3 is greater than this particular one, that is for player B. And similarly, this 2 is greater than the player B strategy. This 3 is greater than the player's 2 strategy. Right strategy of player B. Okay, so in this case, I'm going to call this as the Nash equilibrium. So a simple problem has two Nash equilibrium in this given case. Okay, now let us go to the equation part of it. Okay, one more important concept that we have to remember here is a Nash equilibrium happens in case of pure strategies. What is meant by pure strategy? Now, I can show you one small example. Okay, now what is pure strategy? if I say that I have a row and a column, right? Okay, either I'm going to choose 5, okay, or I'm going to choose, okay, let me say the other one is -3. Similarly, here it is -4 and 4. Okay, so here, as per the Nash equilibrium, when I say it's pure strategy, either I will be playing this value, the strategy A, or I'm going to play the strategy B. Okay, but I don't have any probabilities associated with it. So when I represent this, I'll just represent 1 for player A, this first value, and for player B, it's going to be 4. Okay, so very simple. Just try to understand what is pure strategy, and you also have something called as mixed strategies. What is pure strategy? If you say that outcome is definite, right? Then that is called as pure strategy. Okay, outcome is definite in sense for player A, I'm going to choose only the first value, which means the higher value. I say that that is pure strategy. And you'll represent the strategy S1, S2 for player A as 1, comma 0. Okay, if you say that, say for example, your poker game and all, right? So if you say that you have probabilities associated with each and every payoff value that you get, right? In that case, that is called as your mixed strategies. Okay, so what is the Nash equilibrium? The equilibrium and the point at which both the strategies are achieving the optimal outputs. Okay, in what case that do you get a Nash equilibrium? In case of pure strategies. What is pure strategies? If you have a definite outcome, right, you don't have any associated probabilities for each and every outcome. That is what is called as pure strategies. What is mixed strategy? When you have for each strategy that you choose, when you say that you associate a probability value with it, that is called as your mixed strategy. Okay, now moving on to the problem solving again. Now you have various forms of representing it. So all these are nothing but the values given to you. You just have to find out whether Nash equilibrium exists or it doesn't exist. Okay. Now moving on to the same prisoner's dilemma problem. So here you're going to find out whether the Nash equilibrium is existing or it doesn't exist. So as I said, if both of them deny, right? If both of them deny that value -1 comma -1, which means actually it's 0 comma 0, they're not going to get any punishment at all. That is your final Nash equilibrium, and that is the best strategy for both prisoner A and prisoner B. Okay, so just to understand what is Nash equilibrium, I'll solve this problem here. But what is Nash equilibrium? Why should you do that? You have to do that just to derive at a conclusion that what is going to be the best strategy for both the players. Okay, so this prisoner A, prisoner B can be anything, right? So as you have seen in the previous problems, this is just player A and player B. These are going to be your strategy 1, strategy 2. These are going to be your strategy 1 and strategy 2 played by your prisoner. Okay, so this is how you have to check. Now, what is going to be your dominant strategies? How do you derive at this particular value? Okay, so that is what you have to find out. Now coming to this first row. Now check for the prisoner A, right? For prisoner A, check these two values. Whichever value is higher, you just mark it in red, or you just select that particular value. So for prisoner A, right? So here the value is 0 comma -2. So the value is going to be 0 is higher. Now compare for prisoner A. So all these first values are for prisoner A. Okay. So compare -4 and -1. So which value is higher? -1 is higher. So first of all, the first values here -2, 0, -4 and -1 corresponds to prisoner A. Then the other value here, prisoner B, is represented by -2, -4, 0 and -1. Okay. So now this is done. So I have taken 0 and -1. Now coming to prisoner B, right? So you just have to check for prisoner B, which is the good higher value instance, which is the good strategy that he can play. So for prisoner B, compare these two values. So the higher value is 0. Now compare -1 and -4. The higher value is going to be -1. Okay, so you just mark this as red. Now the value wherein both the values are marked. Okay, so that is for prisoner A and for prisoner B. Both these two values are marked, which means that is going to be my optimal strategy for both prisoner A and prisoner B. So I've put a star for that. Okay, so which means that this is the Nash equilibrium. What it corresponds to? Deny. So this Nash equilibrium is going to be the optimal solution for prisoner A and prisoner B. So they both have to deny. Okay, so that is all about Nash equilibrium. So a simple problem, you'll be given a payoff matrix, and then you have to find out the dominant strategies played by both the players A and B, and if there exists a Nash equilibrium, which means a optimal strategy for both the player A and player B. You have to find out those Nash equilibriums. You can have one or more Nash equilibriums. Okay, so that is all about it. So this completes this small problem of finding out Nash equilibrium in a pure strategic game. Okay, now moving on to the next problem here. Now you have to find out, these will be your exercises. So just two I have done, these two you can do it at home. Okay, so you just have to find out the Nash equilibrium for two players, Henry and Jane. They are two playing with some strategies here. So you just have to compare the higher value 8, then coming to this, the higher value is 7. So this is for Jane. And then for Henry, right? So for Henry, you have to compare these two values. So 7 is higher and 8 is higher. So you mark star for this and you mark star for this. So either you play, Jane plays U and Henry plays L. So that's an optimal strategy. And Jane plays D and Henry plays R. That is also an optimal strategy. So you have two Nash equilibriums. Got it? So that is how you find out the Nash equilibrium, and here you have only fixed probabilities, which means it's a pure strategy being played. Okay, either you choose this U and L, or you don't choose this strategy at all. So this will be 0 if you're not choosing it. So here what happens, you're choosing this U comma L, so that strategy is 1. U comma R strategy is 0. D comma L strategy is 0, and D comma R strategy is 1. So 1 0 0 1 will be your final value of the pure strategy. Okay, and similarly coming to this, I think you can do this. So compare these two. So you'll be having 10, and comparing these two, you'll be having, I'm sorry, comparing these two, you'll be having 2. I think I've gone wrong here, right? So the first value, right? What should I get here? Can someone answer what is wrong here? Which one should I make it as red? For the first player, KFC will have KFC as my first player. So what should I make? I should compare 9 and 10. So which one should I mark it as red? Yes? Can someone answer for this? So everything is black. Students applying for masters, you have to answer these. Without this, you cannot proceed. Especially most of you have applied for data science, artificial intelligence. Come on. So which one should I choose for player 1? Now let us assume the player 1 is KFC and the player 2 is McD, right? So the strategies they choose is UDLR. So first player, I have to compare 9 and 10, and I have to mark red as the good strategy because the profit is higher. Then coming to these two strategies, I mean 1 and 2, the strategy that I choose is 2. So that is for player 1. Coming to player two's point of view, right? So I can choose 9 and 1. I have to choose 9. And similarly, 10 and 2, I can choose 9 and 1. Oh, sorry, 1 second. Not this. I have to compare it with row wise, right? Sorry. This is black. 9 and 1. So I'll get 9 as my optimal strategy. So I compare 9 and 1 for this U. That is for player 1. And for D, I compare 10 and 2. So for player 2, McD, I have to compare 9 and 1. So I get this 9 here. Then this right strategy, if I play against U or D, I can play 10. So I have to choose 10 versus 2. So 10 is going to be my higher value. So if I have something like this, I will have 9,9 as my Nash equilibrium. So player 1 has to play U and player 2 has to play L. Got it? So this is going to be my Nash equilibrium. Now coming to this, for Pepsi, which is going to be the strategy being played. Can someone quickly answer? 6 and 4. So I have to choose
6, ma'am.
Very good. Then 7 and 3.
7.
Perfect. 7. So this is for Pepsi, right? And Coke is going to play two strategies, L and R. So L played against these two strategies. So what should I choose? It is 8. And here you have a tie. So 7, 7. So randomly you can choose 1. So if I choose 7, so this is going to be my payoff. So this is going to be my Nash equilibrium. Okay. And finally, for this, for player A, it is 7 and 5. So that is going to be 7. Then it's going to be 6. Right? So U strategy when compared to these two. And similarly, B strategy when compared to A. So 6 and 5. This is going to be my Nash equilibrium, right? So that is all about finding out Nash equilibrium. As told earlier, you can have more than one equilibrium values. Next, we are moving on to decision making. So, which means, as I told you earlier when we started, you have the players. The players are called as rational players, which means they know everything about the game. At least everything about the game, in sense they don't know the rules of the game, how to play it. Okay. Now, what you have to do is, now each player is rational and he can make its own decision. Okay. Now you have to tell how does the player behave rationally, or how do you say that he is rational. You need some justification mechanism. Only then you can say that he is going to take rational decisions. Okay. So moving on to mechanism design. So this is a very important concept in game playing, right? So mechanism design is nothing but how do you design the game, or it's also called as game engineering. Okay. So I'll give you a small example of how do you implement a social choice function, which means mechanism design, right? So for example, this is a very famous problem wherein you have a cake. So the cake has to be equally cut, right? So that both kid 1 and kid 2, they get equal halves. Not even 10 or 5 milligrams extra piece of cake should go to each and every kid. Okay. So this mother happens to be the social planner here. And how does the mother behave as a rational agent implementing this mechanism design? This is going to be the question. Any guess? How can you cut the cake into equal halves, two equal halves, so that each kid gets exactly the same amount of cake, right? So how do you say that the mechanism designer here, the social planner, is going to be a rational agent and going to make the best decision? Can someone answer for this? Kid 1, you call it as a rational agent. Why? Because he's smart enough. By looking into the cake itself, he'll tell whether he has got exactly equal portion of the cake or whether the other kid has got a slightly higher portion of it. So how can the mother be a social planner for this? Yes, I expect some answer.
Cut them into vertically, man.
Okay. If you cut it vertically, this kids might have some thought that because they're not going to weigh the cake. Okay. Think beyond the usual logic that you have to think. You don't have a weighing machine, but then you have to satisfy both the kids. And not necessarily the mother has to cut the cake. Okay. Can you design mechanism? Design is nothing but you have to design a strategy so that both the players are satisfied. That's all. What is the strategy that the mother is going to play? No answers? Okay, I'll tell you now. So the mother is going to ask one of the kids can cut the cake and the other kid is going to pick the cake. Okay. So what happens here is when I am this kid 1, I will make sure that the cake is exactly half. Okay. So that the other person obviously he's going to take the bigger piece only. Okay. If I cut it slightly smaller also, obviously the larger portion will go to the second kid. Right. So I'll be careful enough so that I will cut it into two equal halves so that the other kid will also be careful enough so that while selecting it, I cut, you take, right? So he will not be questioned because anyway he gives the liberty for the other kid to choose the bigger choice. Okay. Now he'll be careful that he is going to get the best piece. So both of them are satisfied. Okay. So this is the mechanism that is being played by the mother. So here you call the mother as a social planner, mechanism designer. Okay. So this is simple strategic decision making. Now here you know the story of Tenali Rama. One baby is claimed by both the mothers. Okay, so this mother says that I am the owner of the baby. The other mother also says, no, this baby belongs to me. Okay, so here, if you have gone through the story, you know what Birbal said. So very simple. He said that cut the baby into two halves, and each mother can have one half. Okay. So what happened was the real mother said, no, no, please don't cut the baby. Let the other mother take the baby. But then the artificial mother, like the one who claimed it artificially, right? So that mother said she never told anything about it. So she was waiting for the decision. Okay. But the real affection, the real mother, she said, no, that's okay, don't cut the baby. So that was actually a kind of a decision making, which we call it as a mechanism design. Okay, so you have to be rational so that both the players are satisfied. Okay, now coming to auctions. So where are we going to apply this game theory? Basically, we are going to apply it in auctions, all your e-commerce applications, right? Without knowing game theory, you cannot enter into the e-commerce applications. So here we have already seen this. You have one seller, multiple buyers, one item. Okay, so which item is that single item has to be given to one seller. Okay, one seller is going to give that single item to one buyer. When you have multiple buyers, obviously, how do you select the buyer is going to be called as your auction. Okay, so how do you implement that auction? The most famous auction is nothing but your Vickrey auction. What is that Vickrey auction? You have bids. So B1, B2, B3, B4 are nothing but your bids. So the highest bid you will select, which is nothing but 80 rupees. One person has quoted the highest bid. So that bid will be selected for that person, but then he has to pay the amount quoted by the third auctioneer. That is the third bid, 60 rupees if he can pay. So that bid will go for him. But then the one who quoted the highest bid will be given the chance to buy that particular item. Okay, all your tenders, e-procurement websites. So they implement these Vikri auctions. Okay, so here 84, this person gets the offer, but what amount he has to pay is nothing but the next bid, which is 60 rupees. So this is typically called as your Vikri auctions. So this is a kind of mechanism design. Okay, so how do you select a particular buyer for a single indivisible item? So that is auctions. For that auctions, the most commonly used auction is nothing but your Vikri auction method. We've also seen several other auctions in, I don't think whether it's last class or before that, we have seen several other auctions wherein we call it as English auction, Dutch, first price auction and Vikri auction. So this is the most commonly used one. So when I say English auction, what happens? You have multiple buyers sitting in one common place.
Ma'am,
Yes.
ma'am, if it's like the first one, if in English auction, if 60 after then they're stopping, no, ma'am. So
Yeah.
the person who won the 60 has to pay 58. Am I right, ma'am?
No. For English auction, the person who has quoted 60 rupees, he has to pay 60 rupees.
Okay.
That's usually they show it in TV and all, right? The
Yeah,
usual
ma'am.
cinema movies. That's a kind. Okay. And for Dutch auction, the seller starts with the highest price. Say for example, for a painting, then he keeps reducing it. If one buyer comes forward to buy for that particular price, so the buyer decides the worth of that particular painting. If they feel that 60,000 is worth for one painting, the buyers will come and buy that painting. But initially, the seller will quote some initially large amount. Then first price auction is, so you have all the auctions. So the person who has quoted the highest price, so he will be the winner of that particular auction. That is first price auction. So these two will be the common tenders, right? Whatever they follow in the government office. But in e-commerce sites, it's this Vikri auction which is mostly used. So what is this Vikri auction? The last quote will be, I mean, the buyer who gives the highest quote will be selected, but then the next quote, next to whatever what was the highest quote, that amount has to be paid by the buyer. Okay, so these are the common types of auctions. So here all these auctions comes under the mechanism design. So that is all about the game playing and knowledge structure. Okay, then moving on to game as a search problem. Okay, now we have seen, I can show you one game, the min-max game. Okay, now very simple. What is that we are trying to do all here is, I am one player, you are the next player. You try to minimize my profit, I try to maximize your loss. Or I try to maximize my own profit. So this is how the game goes. Okay. So how do you play tic-tac-toe? You will play in such a way that you have to maximize so that you have to win. Okay, you have to get all 3x. And how do I play? I will play in such a way that I will not allow you to win. Okay, so this is a typical min-max strategy. And why do you call it as a game as a search strategy, right? So starting from the initial solution, you have to reach the goal state. Okay, what is the goal state? Either you lose or you win or you draw the game. So either of these three states you have to come. Okay, so when you come to all these three states, so it's either -1 or +1 or 0. So the path you choose from the initial state to the goal state, what is that goal state? The winning state, this +1. What path you choose, you are actually searching the tree. Okay, so that you call it as your search tree, game as a search tree. Okay, so similarly for any game that you choose, from initial state to the final state, if you can derive a path, or if you can say that one state changes from, I mean, there's a state change from one state to another state, right, until it reaches the goal state. In that case, you call that particular game as a search tree. Okay, so here, what is the concept we are going to deploy for showing this particular game is nothing but you have only the min-max strategy. Okay, so what is min-max strategy? First, X is going to play. So X will try to maximize its revenue or maximize its, we talk in terms of payoff or utility. Okay, so whenever you write, you just have to use these terms, payoff, utility value. So all these represents a gain that is going to have for the max of X. Okay, now X has played whatever all the possible moves wherever you can have. So you can have maximum of 9 places. So 9 moves you have placed. Now you O has to play. When O has to play, what is that? It has to play in such a way that it is going to minimize the gain of X. Okay, so it is placing O in such a way that, okay, now here you cannot find much difference. So you are going to randomly place one value. Since X is here, we are going to just elaborate on this. So O has been randomly picking up 3 different places. Okay, now let us assume. Now again X has to play such that it has to maximize its own payoff. So X has played. Now O has to play. When O has to play, what happens here? O has to play in such a way that, okay, it has to put one O here. Only then, right, it has to minimize the gain of X. That is my first intention. Before you say that I have to win by putting a O here. Okay, next move I will think that I can put a O here. No, but I have to, O has to play such that X gain is minimized. Okay, so immediately I'll put one O here, right? So this is how I play. Got it? So this game is minimize the maximum strategy such that each player tries to maximize its own payoff and minimize the payoff of the other player. Okay, so this is a typical min-max strategy. Okay, now coming to the algorithm part. Okay, now you have understood how to play XO game. So the same min-max algorithm, when I'm just representing it as a tree, so all my leaf nodes will have my payoff values. Just as we had +1, -1 and 0. These are called as my utility values. So here I am representing it in the form of some values, positive or negative values. Okay. So what is max min max strategy? So here I have to choose a max of these two and 3. So that is going to be 3. Okay, max value. So among these two, 5 and 9, it's 9. Then 0 goes up. Here 7 goes up. And 2 and 1, 2 goes up. 5 and 6, 6 goes up. Okay, then I have to play a min value. What is min strategy here? So it has to be the minimum of these two values. So when I say minimum of these two values, it's minimum of 3 and 9. So 3 has to go here. Okay, so we'll see. This game is not complete. Yeah, right. So this is going to be the minimum value which goes up 3. Minimum of these two 0. Minimum of these two is 2. Again, max has to go up. So what is max of these? It's going to be 3. Okay. So once you have this highest value of 3, now what is the path? Path is A, B, E and M. This is going to be my search path. Okay. So, oh, sorry, 1 second. Okay. Now going back. Okay. So this is going to be your min-max rule. So you have to move in such a way that you maximize your payoff and you minimize the gain of the other person plays in such a way that it minimizes the gain of the other person's strategy. Okay, so this is what is called as your game. And what is that backup value? For max node means you have to choose the maximum of the associated with its children, and for the minimum node you have to choose the minimum values associated with its children. That is what is your min max tree. Okay, so create a node as max. This game we have already played. Okay, so what is backup? You have to choose the minimum or maximum, right? So so here you have the values. So these two are children. Depending on how you name this, either you have to name this as maximum or minimum. Okay, so depending on how you name it, you have to back up the values. So here black node is minimum, so I am backing up 2. Among the children node, I have 2 as my minimum. So among 1 and 8, I have 1, because black node is defined as my min node. And among these two, again I take 2 as my max node. And this is my min max path, wherein to achieve this 2, starting from my root node, I take this particular path, that is this violet, this 2 and this 2. Okay, so this is the final move starting from my initial root node to my leaf node. Okay, so that is all about my min-max search. So when they ask you to write about game as a search tree, you have to just explain the min-max algorithm, and you have to show it with a small example. In terms of game playing, the example that we have seen is EXO game. Okay, so the common properties, whether it is complete, yes, if the tree is finite. If it is optimal, yes, because you always find a solution. Time complexity and space complexity for a general search tree, depth first search tree. So it's going to be order of B per M, order of BM. So the usual DFS complexity has to be written. Okay. So till this, it's all about my min-max algorithm. Now, before we move on to the alpha beta pruning game, I just have one few more game theory problems. Okay, we'll come back to alpha beta problem pruning later. I'll just skip this for now because we have 15 more minutes. Okay, we'll go back. I mean, we'll complete this game theory problems because we have already seen what is saddle point. We've already seen what is strategies, what is payoff, what is Nash equilibrium. Okay, so to solve, I mean, using all this, we've also seen how to solve a zero sum game. So when they say just the topic here is game theory problems, right? So you just have to use all this to show the different types of game theory problems. Okay. Okay. Now, a few problems we'll just discuss. So you have the game X strategy and Y plays some strategy. For advertisement, they use radio and newspaper. This player also uses radio and newspaper. As a result, they get the payoff matrix. Okay, so once they get the payoff matrix, you have to decide whether they have played an optimal strategy or whether they have not played an optimal strategy. Okay, so game outcomes. How do you read that payoff matrix? Okay, so here you read X1 uses radio, which means the payoff is 3. Y uses radio, the payoff is 3. So this is the way in which you read the strategy. So if X uses radio, Y uses radio, X is having a plus 3, which means what? For X it's going to be a plus 3 and the payoff for Y is going to be a loss, right? So that is Y loses. And similarly for the next one, X is going to have a payoff of plus 5 and Y it's going to be a loss of 5. And for X2, X is going to be plus 1 and this is going to be minus 1. And for Y2 using newspaper, it's actually a profit for Y and it's going to be a loss for X2. Okay, so that is what this is just an interpretation of games, the outcome that you represent using your payoff. Okay, then coming to the okay, so cake cutting problem. What is that? I cut and you choose. That is a strategy which we call it as. This is again a game theory problem. I cut you choose is a strategy which is being played by the mother. Okay, so cutter will maximize the minimum the chooser will leave him, and the chooser is going to minimize the maximum the cutter will get. Okay, so this is the strategy that we play, which is min-max. So as I told you, the X goal is to win, and Y goal, I mean the O goal, XO game, right? O has to play in such a way that X does not win. Okay, so this is the min-max criterion. Okay, so that is again a game theory problem. Then coming to these problems here. What is a saddle point? So saddle point is what? You have to choose the minimum of rows, and you have to choose a maximum of minimum, right? So the profit should be minimum. You cannot initially assume the highest profits. So choose the minimum profits, and maximum of minimum should be your assured amount. Similarly, choose the maximum loss, right? And the minimum of the maximum will be your value. So if min-max is equal to maximum, that happens to be your saddle point. Okay, so this saddle point exists for a pure strategy. What is that pure strategy? Either you play that strategy or you don't play that strategy. Okay, but you don't have any probabilities associated with it. That is called as your pure strategy. Now, why did he name it as saddle point? Who named it? Von Neumann identified this concept, and he has named it as a saddle point because he has chosen the saddle-shaped mountain pass, and he says something saying the maximum elevation reached by a traveler going through the pass to get to the other side, and the minimum elevation encountered by a mountain. Okay, so this is the reason behind naming it as saddle point. Okay, so we have already seen this. For a pure strategy, you have to choose max of min and min of max. Okay, so if both are equal, then you call it as a saddle point. Then coming to mixer strategies, yeah, this is what I want to convey now. What is mixer strategy in game theory? I told you that you are going to associate some probabilities with each and every strategy. Either this will be completely played, or you're going to associate a probability between 0 to 1. What is that called as P? The probability of playing y2 is 1 minus p. Similarly, probability of playing x1 is q, and probability of playing x2 is 1 minus q. So totally you'll be having two expected gain. So 4p plus 2 into 1 minus p. Here you get 1p plus 10 into 1 minus p. So again here it is 4q plus 1 into 1 minus q. That is for y1. And similarly here it's 2 into q plus 10 into 1 minus q. You have these two values here and these two values here. For a mixed strategy game, associate a probability with it. Then you just have to solve these two equations and these two equations so that you get the expected payoff. So how do you do that? So 4p plus 2 into 1 minus p. So you equate these two values, right? And similarly equate these two values. So what do you get? You get the value of p, right? So once you get the value of p and q, you just have to substitute it back in that equation so that you get the expected payoff. Okay, so hereafter whenever you use mixer strategy, you don't call it as a payoff, that is termed as expected payoff. Okay, so when you replace that value of p back in that equation, 1 plus 10 minus 10 into 1 minus p, so when you just replace it, so this is going to be your expected payoff. And similarly, when you replace that value of p in this equation, this is going to be called as your expected gain for x1 strategy. Okay, so similarly here, if you replace q in terms of this, this is going to be your expected loss for y1. Again, this is going to be an expected loss if you replace q in this equation. So expected loss for y2. Got it? So this is the only difference between your pure strategy and your mixed strategies. So when I say mixed strategies, immediately you just have to remember that you have to associate probabilities for each and every value. Okay, so here again you have one more problem. Probably you can solve it at home. So you have x1 and y1, x2 and y2. Just associate probabilities with these and find out the expected gain for rows. So always remember it's going to be the gain for rows and column is going to be the loss. Okay, so column wise expected loss. Okay, so same method, you just have to apply expected gain and expected profit, loss. Okay, so find the values of p and q, substitute it, you will get the value of expected profit and loss. Now I want you all to answer some problems in game theory. Okay, this is actually solved. No, not solved. Consider the following prisoner's dilemma game. Okay, player 1's payoffs are in bold. So here, okay, all player 1's payoff are in bold. Now tell me which is going to be your dominant strategy. Explain the Nash equilibrium of the game. Start with player 1. If player 2 chooses cooperate, player 1 should choose cheat. If player 2 chooses cheat, player 1 should also cheat. Player 2 chooses cheat, player 1 should also cheat for $5. Okay. Right. So start with player 1. Okay. So we'll start with this player and you just tell me what is going to be the optimal strategy. Whether there exists a Nash equilibrium or not. Now quickly tell me what is the Nash equilibrium here. Can someone give me an answer for this? So player 1 strategy they are asking. Okay. So how do you do that? Compare 10 with 0 and 12 with 5. So obviously you'll be
10 and
having
12. Yeah, ma'am.
very good. Perfect. Then uh, player
Need to
2
compare player
chooses
2, no,
cooperate.
ma'am. Next one.
Yeah. For player 2, how do you go? 10 and
To 10 and 12, 0 and
12.
0
Yeah,
and
10 and no. For player 2, it's going to be which value should I highlight? 10
it
and
says that player 2 chooses to cheat, no, ma'am. So 12,
yeah, 12. Okay.
one should also cheat means in 5, 12 and 5, ma'am.
If player 2 chooses cooperate, player 1 should choose cheat. This is the answer given. No. First of all, generally solve it. No, we'll see what is the Nash equilibrium that we get. So for player 1 strategy, if we choose, it's going to be 10 and 12. Okay. So 10 and 0, you'll choose 10. 12 and 5, you'll choose 12. And when you come to player 2, it has to be um, 10 and 12. So it is going to be only cooperate. Cooperate is going to be the Nash equilibrium, right? But why is it given as player 2 chooses cooperate, player 1 should choose cheat? Player 2 cooperate, player 1 cheat. 12 versus 10. Okay, player 2 chooses cheat, player 1 should also cheat. 0 versus 5. They're starting with this, it's a that's okay. Anyway, we are also checking like that only. Okay, if you leave this part alone, if you check what is each player's dominant strategy and explain the Nash equilibrium of the game, 10 comma 10 happens to be a Nash equilibrium, right? This part, why they have given who has to start the game, probably I'll check this part and let you know. Why they say that they have to start with player 1. Starting with player 1 also fine. So in which case we compare 10 and 0 and 12 and 5. And when it comes to player 2, chooses cheat. So when you compare player 2, it's again 10 and 0, 12 and 5 you have to compare. That's the usual method how we do it. Why should they specifically give it? That is my question. Anyway, that part will you need not consider. This part just ignore. Just answer for each player's dominant strategy. It's already
10 and
given.
10 and 5. Sorry, 10 and 0, 12 and 5, ma'am.
10 and 0, yeah,
For
10 and 0, 12 and 5, right? So, no. Nash equilibrium is 10 comma 10, right?
yes, ma'am.
Okay. You're talking about dominant strategy.
Yes, ma'am.
So anyway, if you see for dominant strategy, 10 and 12 is higher than 0 comma 5, right? Perfect. So you mean to say that you will delete cheat, correct? You'll
Yes,
keep
ma'am.
only cooperate 10 and 12. And coming to column wise, if you check which is dominant. So row wise dominance, cheat can be deleted, and column wise dominance, mm, okay, maximum loss 12 and 5. So which column should I delete? 10 and 0 or 12 and 5? For column dominance. Maximum loss has to be deleted, right?
12 and 5.
Yeah, that is higher than this value. So earlier what did I delete? Okay, cheat has to be deleted. Here also cheat was deleted. Now you are left out with only,
Cooperate.
yeah, cooperate, 10 comma 10. Okay, actually we have not arrived at 10 comma 10 using the dominant strategies yet. We have derived at 10 comma 10 using the Nash equilibrium. Okay, but still when they ask you to say that what is each player's dominant strategy, for player 1 it is cooperate, and for player 2 also it's cooperate. That is my dominant strategy. Okay, then moving on. Right, you have this rock paper scissor game, right?
Yes,
So
ma'am.
rock crushes scissor, paper covers rock, scissor cuts paper. Okay, now you just put it in the form of a matrix. Okay, matrix is not given. Okay, so what we can do is, let us assume two players are playing this game, player A and player B. So the strategies played by player A is he can either choose rock or paper or scissor. Similarly, in the column matrix also, player 2 can choose rock or paper or scissor. Okay, so when rock and rock, when you have, what is that? +1 or -1?
Ma'am, can you repeat me? Rock and
Rock and rock. You'll be having a table here.
neutral only. No. Like no plus or no minus.
Zero, is it?
Yeah, ma'am.
Okay, so first of all, we have to draw the table once again.
Stone,
And
paper,
after,
scissors. Yeah, ma'am, both same. Yeah.
um,
Stone means neutral only. No,
zero you'll put.
both of them no points.
Okay, rock and paper means?
Uh, Paper gets the points because the rock covers the paper.
Okay. So what you have to do for this game, you can take it up as an exercise. So you just have to put a table. Okay, so this is player B, rock, paper, scissor. Similarly for player A also, rock, paper, scissor. So rock and rock, probably you said one, is it?
No, actually no points, ma'am.
No
Neutral.
points. Okay. Rock and paper, who gets point?
Paper, ma'am. 1 point. 1 point for paper.
Okay. So usually, right
Here means here we
here,
are considering as rock only first, no, ma'am. So same. I think -1 should come in.
yeah. See, when you put +1 here, it means that for rock the point goes, and for paper it's a loss. Which one should I put?
You should put -1 only, no, ma'am, because like it's
Which
rock.
means what? Paper gets the point.
Yeah, paper gets the point.
Yeah. Okay. So you have to
Rock
put
versus
-1.
scissor, rock gets the point, so +1, ma'am.
So +1. Okay. Then paper versus rock, who gets the point?
Paper, ma'am.
Paper. Okay.
Yeah.
So if it's paper means it's +1. Then paper,
0 neutral.
0. Okay. Paper, scissor.
Scissors get the points, ma'am. So -1 for paper.
Okay.
Rocks get the points for scissors, so it's -1, ma'am.
-1. Okay.
+1 for paper. Scissors, 0.
0. Okay. So indicate -1 if you lose. Okay. Write down the strategic matrix form of the game. So this is your strategic matrix form of the game. What is the Nash equilibrium of the game? How do you find out the Nash equilibrium of the game? So very simple. First of all, if you can eliminate the dominant strategies, try doing it. Otherwise, if you cannot eliminate, okay, just try if you can eliminate. If you cannot eliminate, then you have to find out the Nash equilibrium. How do you do that? Nash equilibrium. So you just have to compare these three values. So which is going to be the best strategy that can be played. So you compare 0, 1 and -1. So the best value is 1.
1. Yeah.
Okay, so you will be taking that. So similarly, you do for other values also. If you happen to have, or else, okay, first try if you can resolve the dominant strategies. Okay, try doing this paper because it's to do exercise. Okay, tomorrow I'll give you the solution for this. And you also have one more problem. This is also to do exercise only. Does each player have dominant strategies and explain the payoff? Okay. Now coming back to this, let's check out if you can have values as rock comma rock, which means for player A the value is 0 and for player B the value is 0, right? For player A it's -1, player B 1. You can also represent like this. Why? Because you have to compare the two rows, and then because here you're not finding out the saddle point. Okay, you have to find out the Nash equilibrium. So in that case you have to compare player A with player B. Okay, so here it is 1 and it's a loss for minus scissor. So we'll put it this way. This is 1 and -1, 0 and 0. It's going to be a
1,
profit for
comma 1.
scissor. Then it's 1,
1 minus 1,
-1,
0.
then 0. Okay. Now check if you have dominant strategies, or even otherwise just check with these values and find out whichever value is the highest. Which means you are selecting the dominant strategies with respect to player A, which means you compare 0, -1 and 1. So the dominant strategy here is 1. And then the dominant strategy for paper, it's going to be 1 here. The dominant strategy for scissor is this value.
1 on the paper. Yeah.
Yeah. And coming to the column wise strategies, which means for player B the dominant strategies, it's going to be here. So here exactly 1, and this is 1, and this is also 1. So do you have a Nash equilibrium for this game? The answer is yes or no. Does this? I don't think so, right? Because nowhere you have got both as red and we have not starred anything.
Yes,
So you
ma'am.
don't have any Nash equilibrium. Okay, just check out whether this solution is right. Okay, then also for this solution, this question, right? So you just have to find out does either player have dominant strategy, explain if there is a Nash equilibrium or not. Okay, so try these two problems as to do problems. Then next class we continue with alpha beta ruling. Okay. Oh, 12, 10. Sorry. Attendance is marked. You all can leave. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Ma'am, when will CD3 will start, ma'am?
Can someone stop recording? It's not coming here for
Ma'am,
me.
when will CD3 start, ma'am?